I'm going to start with number 17, and that is skipping a few problems. That's just assuming that you can put numbers in order from least to greatest, which I assume that I can safely assume. Also, numbers 11 through 16, you're identifying different properties, which I think you can do. Now we're going to actually use the properties to prove some stuff, and we have to write down and justify each step, kind of like a two-column proof, like you might have seen in geometry. So let's see if we can figure out. We want to show that this can be written as 2 times a. And we have to use all the different properties. So let's see. Maybe let's rewrite this using the definition of multiplication. So 6 times a times 1 over 3. Now it's multiplication. We're just going to rewrite this side so that it eventually looks like this side. So we'll put definition of division. Okay. And then we'll just say let's do 6a, group those together, and then multiply that by 1 over 3. What property did we use there? We used, well, first a was interacting with 1/3, and now a is interacting with 6a, and it's all multiplication. So this would be the property of multiplication that is called associativity, or the associative property. Okay, so we used associativity, or the associative property, to rewrite this way. Then we could say, let's make it a times 6 times 1/3, and that's using commutative, the commutative property. These switched places, they actually moved. They went somewhere. They commuted. So there you go. Maybe let's do a times 6 times 1/3. Okay. I'm going to be really strict here. I wouldn't expect you to do this, and we will never do this again in math, to go through this so step by step. But used associativity again. You may not have to write down each step, but you do have to. You do have to be able to think this way. That's the important part. We can just break this down to the factors of 2 and 3. Factor of 2 and 3, 3 times 1/3. Okay. So we just factored. And then 3 times 1/3. Well, that's 1/3 is what's called the reciprocal of 3. It's also called the multiplicative inverse of 3. 3 times 1/3 is 1. So a times 2 times 1. Okay, so that we would say multiplicative inverse. That could work. And 2 times 1 is just 2. So you get a times 2. That step we could say was multiplicative identity. And then a times 2 is the same as 2 times a. And that we would say is commutativity. And there we have it. That was commutativity. And we have 2a, just like we wanted to show at the very beginning. Kind of silly in a way, but then again, not silly. You need to be able to think in these terms, in the terms of you might jump 3 or 4 steps ahead in this process, do them all in your head, but they have to be done correctly. Your brain will be just firing, away super fast, and applying all of these properties 2 and 3 and 4 and 5 at a time, but it needs to do them correctly. So while you won't write them down step by step, your brain needs to be able to do them step by step. Okay, if I were to have started out at the beginning and said, oh, 6 times a third, that's just 2, so 2 times a. Well, I just did all of this stuff all in my head, because what I did was I recognized that I can multiply 6 times a third, and that order is not important when I'm multiplying everything together, which means that I first took 6 and put it over here, realizing that the commutative property is at play, and I jumped all the way down to here and recognized that there's a factor of 3 in 6, and that 3 times a third is 1, and so the 3 and the 1/3 cancel each other out, and I'm left with just the factor of 2, and that I can then switch 2 and a, so that 2 times a, it's in that order. You're doing a lot of stuff, and you need to do it correctly. You need to recognize that all of these properties are being applied, and you need to apply them correctly. So while you won't write them down every time, you will use these steps, each one of them, every time, and it just needs to be right. So it seems silly, and it seems overkill, and it is overkill to write it down every time. If we wrote this down every time we did a problem throughout our entire career, calculus would be, well, bad. It would take a long, long time to do just one problem if we wrote down everything and justified each step. Where most of the time you're going to do this in one step. You're going to say 6 times 1/3 is 2. 2a. There you go. It's proven. That's enough on that. It's enough rambling. Let's do another 19. Why not 19? So we want to prove that c minus 3 plus 3 is equal to c. Yes. Okay, so let's call this c plus negative 3 equals, oh, we don't need to write that. What's our justification for doing what we've just done? We could call that definition of addition, or of subtraction. Excuse me. Definition of subtraction, addition of the opposite. Then let's say c plus negative 3 plus 3. That's called associativity, or the associative property. And then negative 3 plus 3 is 0, because 3 and negative 3 are additive. Additive inverses. Okay, and c plus 0 is just c, because 0 is the additive identity. Okay, again, if you see this problem just sitting here and you want to clean it up a bit, you're going to say, well, obviously I could just take negative 3 and add it to 3, because it's kind of like these parentheses aren't that important, because it's all addition, really. We recognize it on the addition subtraction level of the order of operations. And negative 3 plus 3 is 0, so c is all that's left. But what you're doing, your brain is doing, since it's so familiar with all these properties, is applying these properties all at once really quickly and seeing that c is left. Okay, and if you skip a step, or you apply a property that doesn't exist, or you apply it slightly incorrectly where it doesn't apply, then you're in big trouble. You need to make sure that you're applying these properties when it's appropriate, when it's legal. Okay. Okay, so let's do another one, 22. 12b plus 15 minus 3b. We want to show that that's equal to 15 plus 9b. We're going to justify every single step. All right. Well, we can see that in the end we're left with a number 15 and then a number times a letter here, 9b. So we might think of, we want to collect like terms. So we need to actually be able to do that. To move towards that, we're going to want to bring 12b over near where negative 3b is so that it can interact with it. So let's put 15 here and add 12b here. Minus 3b, what did we do? We used the commutative property. Okay. And now we want to have 12b and negative 3b to interact. Can they? Yes, because really this is the addition of negative 3b. I'm just going to throw that in there. We could put slash definition of subtraction. Okay. And then do 15 plus 12b plus negative 3b. All right, so that was the associative property. So that's great. So now we just don't have the notion of combining like terms, technically speaking, in this section. We're kind of defining the ability to collect like terms, quote like terms. And here's how we can do it. We can use this beautiful thing called the distributive property, either in forwards or reverse, either way we want to. We see we have a common multiple here, this b, and I was going to get really OCD about it, but I'm not going to. So we could say that this was the result of taking b and multiplying it through 12 minus 3. We would just distribute this b to 12 and to 3 to negative 3, and then we would get this guy up here. Okay, so this is the distributive property, which is a wonderful property. And 15 plus now 12 minus 3, we just have addition and subtraction. We know these things. B times 9. All right. That we could call that closure. When we add numbers together, which that's what we're doing, 12 plus negative 3, then we get another number. We get one of those other real numbers. And this can be written as 15 plus 9b, because b times 9 is the same as 9 times b by the commutative property. Okay? So there you go. Every step justified. Again, if we were going to approach this from the very beginning, we would just kind of say, like, I don't really need to write these parentheses. I can see 12b, collect like terms. 12b minus 3b is 9b, 15 plus 9b. Easy. But what you did was apply all these properties. Whether you thought about it very hard or not, you recognize that all these things are possible. That 12b can interact with negative 3b. Even though I'm adding it to 15, I can just throw it over here. And that I can treat these like terms is really an understanding of the distributive property. Just all this stuff you're applying that you don't realize. And if you are applying it incorrectly, then you're in trouble. And you just want to be sure that you don't make those little mistakes. Okay. So let's see. We'll do number 31 to start with, at least. This is a really important skill to have, converting between units. And we call it dimensional analysis. Usually, if you hear that word, that's what that means. It sounds really cool, but it's really just converting units. So 350 feet per, oh, not even that, just 350 feet. We're going to convert that to yards. We have to go from feet to yards. Okay, so the crux of this is basically canceling things out and using really convenient fractions. What I mean by a convenient fraction is a fraction that equals 1, because what we're really doing is using the multiplicative identity. If we multiply by 1 here, we haven't changed what this number is actually worth. If I multiply by 5 over 5 or 10 over 10 or 7 over 7, it hasn't changed what this is worth. It's worth the same amount. And so what we're going to do here is multiply it by a form of 1, a convenient form of 1. And why it's convenient is because the denominator is feet, so we cancel out this unit of feet. So we can just go ahead and know that's what's going to happen. And yeah. And now we just need to fill in the number so that the fraction is equal to 1. And we want to wind up having yards. So we need an equivalent amount of feet to yards. Well, I know that there are 3 feet in 1 yard. Okay, so we get 350 divided by 3, or 116 1/3 yards. Okay, so that's the basic idea there. Let's just jump to 38. Just all the way to the end there. We want 6,800 seconds to be converted to hours. Let's go better than that. Let's convert it to years. I'm just changing this problem. This is 38 remix. 6,800 seconds to years. Okay, well, I don't know how many seconds are in a year. If I did, I could just take this fraction, multiply by just like we did here, something that has an equivalent number of seconds to years. I don't know that conversion, so I'm going to have to take it step by step. So this is going to be seconds. What do I know about this? I know seconds in a minute, so I could do that. There's 60 seconds in a minute, so now I've canceled out my seconds unit. And of course that's 1 minute. Okay, well, how can I go from minutes and get closer to years? Let's see, minutes in, I know minutes in an hour. I was going to try to go to a day, but I don't know how many minutes are in a day. So minutes in an hour, there's 60 minutes in 1 hour. Okay, so now I've gone a step closer. I've canceled out the minutes there. I converted this to minutes, and then I converted the minutes to hours. I'm going to convert the hours to, I only know how many hours are in 1 day. So let's say 24 hours in 1 day. Okay, so now I've canceled out the hours. I'm in days now. All right, so now can I go from days to years? Yeah, I know how many days are in a year. Okay, 365 days in 1 year. Okay, so now all I have to do is take 6,800 and multiply it by 1/60th, and multiply that by 1/60th, and I have that answer here because I have the teacher's edition. That's 1 8/9, and then I have to divide that by 24, multiply it by 1/24th, and then divide that by 365. And it's so small that my calculator doesn't even recognize it as a fraction. I can't get it to give me the answer as a fraction, so we'll say it's 0.0002. Yes, 216, say 216 years. So 6,800 seconds is 0.000216 years long. So there you go. Just another crazy example. All right, that'll do it. Thanks for watching.